So these are adders. You would have to actually remember the shapes. So all those circuits which take two inputs and produce sum and carry as output are called adders. If they are taking two inputs, then these are called half adders. If they are taking three inputs, A, B, and C, they are called full adders. So you can see here as C in and C out. I have not made it outside, it is inside, but that really does not matter. Still, this circuit has got three inputs and this circuit has got two inputs. All right, so those circuits which lie inside ALU and they are responsible for adding and adding integers only. I told you that real numbers are dealt by the computer outside ALU in floating point unit, and integers are dealt by this ALU, and these are two circuits which add bits. All right, you would have to remember these shapes better. All right, you might be asked to draw these circuits. So those which take two inputs are called half adder, and those which take three inputs A, B, and C are called full adders. Now, if you pay attention to this, these are two inputs, these are two inputs. So this is A and this is B. So the result that is being produced on the right, you have got sum, on the left it is carry. So a circuit which is taking two inputs here and producing sum and carry, although you don't see carry over here, but still there is a carry. As I said, that the bit is always there, so carry is there. All right, so those circuits which take two inputs and produce sum and carry are called half adder. Now, if you look at this particular addition operation, you can see that these two bits are being added. This is sum, and there is no carry, but there is zero carry. If you add these two, you would have this sum and one carry. Now, when you add three, these three will not be done by half adder, rather they will be done by full adder. So you need to understand the whole operation is not being taken into consideration, only the columns. Bitwise operations are being taken into considerations. All right, so if there are two bits which are being added, then half adder is being used. So you can see that throughout this 8-bit addition, these half and full adders are being employed again and again and again and again, for every column of bitwise operation. All right, so they are being used several times for even an 8-bit addition. Now, if you could look at this full adder, you can see that at max you would be having 1 plus 1 plus 1, so that is 3. So this is actually sum, this one is carry. So when we add 1 and 1, this is 2, this 0 is sum, and this C is carry. So you can see that answer is in 2 bits. 2 bits. First bit with power 2 to power 0 worth 1, and second bit is with power 2 to power 1 worth 2. So these are 2 bits in answer. Now get back to the previous screen now. Now you can see the truth table is not the ordinary truth table with the ordinary circuits. These truth tables are actually not showing any working. You don't have to show any working. You would only have to show the result directly. So if you add 0 plus 0, I am actually here. If you add 0 plus 0, sum is 0, carry is 0. If you add 0 plus 1, sum is 1, carry is 0. If you add 1 plus 0, sum is 1, carry is 0. Pay attention to it better. These are addition operations. Inputs are presented in the logic truth table the way they are, but the answer is actually as per their operation, cutting out the working in between. There were questions in AS and O level where there was working. Obviously, if you work, so you would have to first have A exclusive for B, and then A and B, and those results will be taken as that. But over here it is directly. So 1 plus 0 is 1, sum is 1, carries 0, and then 1 plus 1 is 2, sum is 0 and carry is 1. Pay attention to it. You would have to remember how to draw them. You would have to remember how to put their truth tables. Now look at this bigger one. If you pay attention, you would see two half adders in one full adder. This is exclusive for this is AND, this is exclusive for this is AND. And these two half adders are being added together with this gate. Which gate is this? OR gate. So do you get it? So a full adder is employing two half adders together and adding them up using OR gate. So A and B are being exclusive for, its output is being exclusive for with C. A and B are being added over, being ANDed over here. And similarly, the result of A and B exclusive for plus C is being ANDed over here. These two results are then being ORed over here to find the carry. So you would have to remember it, how to draw it. And now let's pay attention to this truth table. This truth table is now having three inputs, A, B, and C in. All right, so A plus B plus C, sum is 0 and carry is 0. A plus B plus C, sum is 1, carry, because this is 0 plus 0 plus 1, so sum is 1. This is 0 plus 1 plus 0, sum is 1, carry is 0. 0 plus 1 plus 1, it is 2, so sum is 0, carry is 2. Okay? Then we have got 1 plus 0 plus 0. Input is usual order of logic gates, output is addition. Now 1 plus 0 plus 1 is 2, so result is 2, 0 and 1. 1 plus 1 plus 0 is 2, result is 0. 1 plus 1 plus 1 is 3, so sum is 1, carry is 1. All right, so we are not looking into this particular logic circuit as an ordinary one, but as an adder. Now, sometimes it is also possible that nobody would tell you that what are these circuits. You would have to pay attention to these. So how would you remember that if they are adders? By having a look at their output. There are two distinctions with these outputs of the circuits. Number one, there are two outputs instead of one. But that can be a common case for circuits which are not adders. How would you then recognize besides having two outputs? By looking at their names. The output should be S for sum and C for carry. So if there are two outputs of any circuit with S and C as their name, they are certainly adders. All right, so I hope that I have made you understand these. So this is exclusive working of just half adder. And then this is, that's it. Okay, so all you need to remember, let me revise it a little. Earlier, the use of logic gates to create logic circuits to carry out specific tasks. We discussed it in much details in O level and AS level. Two important logic gate circuits used in computers are half adder circuits and full adder circuits. Half adder circuits, one of the basic operation in any computer is binary addition. The half adder circuit is the simplest circuit. This circuit carries binary addition of 2 bits generating 2 outputs, sum bit and carry bit. The sum bit, the carry bit. Consider 1 plus 1 will give us 1, 0, denary value 2. The 1 is the carry and 0 is the sum. All right. So this figure shows how this is often used in graphic forms, and this logic circuit over here, and this truth table over here is actually making it clear. Uh, the half adder is unable to deal with addition of several bits. For example, 8 bits, more than 2 bits, it cannot. All right. So more than 2 bits, if there are 3, we use full adder. Okay. Now, in this case, if you pay attention, this particular bit, is actually the output do you see what is C in? Hold on. Not this, sorry. A exclusive for B. 0 plus 0, 0, 1 plus 1, 1 plus 1. A exclusive for B. The input for one double zero one. What I'm trying to imply over here that whenever we add, I told you that this full adder is actually the combination of 2 half adders. So for that I would have to make a new table, but I want to tell you that the carry output is being added to the to the result of exclusive or of previous. What does it mean? It means that एक जो half circuit है उसका एक result आ रहा है from exclusive or, the other result is coming from AND gate. So the exclusive OR output is being used as input for the next circuit. This is what I'm trying to tell. And the result is sum. Whereas with addition to the third input, C is being ended to be ORed with previous carry to find the carry output. हमारे पास एक हाफ एडर है और हमारे पास एक ये हाफ एडर है. These are 2 half adders और हम अगर इनको आपस में सम कर दें तो हमें फुल एडर मिलेगा. ये बस बताने की कोशिश कर रहा था. Alright. So this has an equivalent logic circuit of 2 half adders being ORed with the अब ये देखें कि फर्ज करें कि ये एक आपके पास हाफ एडर है और दूसरा ये आपके पास हाफ एडर है. अगर हम इसके अंदर लिखें हाफ एडर और इसके अंदर भी लिखें हाफ एडर तो ये 2 हाफ एडर हमारे पास आ गए. अब इसके अंदर अगर हम एक A इनपुट देते हैं और इसके अंदर अगर हम एक B इनपुट देते हैं तो जो इसकी आउटपुट है पहली वो इस हाफ एडर में चली जाती है, ऑलराइट। और फिर हम एक और इनपुट देते हैं सी इन की, इसकी जो इनपुट है वो भी इस हाफ एडर में चली जाती है, ऑलराइट। अब इस हाफ एडर, सेकंड हाफ एडर की जो पहली आउटपुट आएगी ये हमारा सम है, and the output of previous half adder it goes to another box, let's call it OR gate. This is not the full what do we say, circuit, rather it's just a gate. So the output from second half adder along with the output of first half adder, when they are being ORed, the result is what? Carry. This is what I was trying to imply, that when two half adders are put together, the output of first half adder enters the input as input of the second half adder. The output of first half adder is being ORed with the output of second half adder, the second output of second half adder, or the carry of the second half adder. The result is the C out. This is C out of the full half adder. So you can conceive it the way you like, but what I was trying to inculcate is that a full adder is made up of two half adders. The output of first half adder is entered to the input of second half adder. The output of first half adder, the second output of the half adder, first half adder, will be ORed along with the output of second half adder, second output of second half adder. When they are ORed, then you will find the final carry. Okay, now this was half and full adder. So what do we expect in exam? In exam we expect three things: definition and circuit drawing, definition and circuit drawing. Number two, they may ask you to explain how the full adder is made up. So you would have to actually explain them that the full adder is made up of two half adders and one OR gate, additional OR gate. Thirdly, they will give you the truth table. Now that truth table may have inputs defined or not. If they have no input defined, you would have to actually put inputs yourself, and there without working, you would have to establish answers as well. Okay, so that's about it for half adders and full adders. Okay, this one is different. One exclusive for has got 3 inputs and there are 3 AND gates and 1 OR gate. Then this one is different, and then we have got a different one over here as well. Okay, so we have got this one is the same one, but different. And then you can see, so what I'm trying to imply over here, look at this one, that look at these are NAND gate based full adder. What I'm trying to say over here, this is not the only way of making which we have discussed, but that is the way, the easiest way. All right, so that is why I was actually insisting at first that you should see that how many inputs and how many outputs are there, and then you would have to pay attention to the name of the outputs. Now let's have a look at these half adders. Half adders, these are half adders made up of NAND logic, and this is made up of NOR logic. This is the one that we have studied the way they were shown. This one is a bit different. All right. Over here, NAND gate based, they are different. Over here, these are NOR gate based with NOR logic. They are different. You can see over here, they both are same, but still their shape is different. So there might be several ways. So what if they give you a circuit? That circuit would have a different shape that you cannot recognize, but you will always be able to recognize the circuit by having a look at the inputs and outputs. If the output is carry and sum, then if the inputs are 2, then it is half adder, and if the inputs are 3, then it is full adder. So